All right, so now we are going to be talking about gauge symmetry. This is the last part of chapter 5. Again, we are going through this book, No Nonsense Quantum Field Theory, by Jacob Schwittenberg. And yeah, so we're in the last part of chapter 5. We're going through gauge symmetry. I've already sort of pre-written a lot of stuff out here because the derivation that I'm going to do in this video is somewhat tedious in that there's a lot of stuff to write down. And so I've sort of pre-written most of this down already just so that I can explain as I go through it instead of having to go through it with the pen. It just takes a lot longer. But anyways, let's get right into this. So we're started. This chapter is on gauge, or this section is on gauge symmetry. I'll write this in. Gauge symmetry. And gauge symmetry is important in that it's going to help us identify Lagrangians that are invariant under some change in a function. And what do I mean by that? I mean that we start off with our 4-vector potential. That's this right here. We've sort of established this already in a previous video, what exactly this 4 potential was. This came out of the Proca Legrangian, where we had the tensor, the electromagnetic field tensor, F mu nu, and then we had that added A mu term in the Lagrangian, where we had where we were interested in looking at the dynamics of the Lagrangian. We were interested in looking at the solutions. So again, this here is the electromagnetic 4 potential. This is a vector. This right here is a vector. And what we want to do is we want to take this 4 vector and we want to transform it. So this is the transformed 4 vector, and it equals the original 4 vector plus some added term, the derivative of some function on the spacetime. Okay, so when we're looking at this, we are saying, well, we have our field, and at every point in the field, we have a value for our 4 vector. So right here, for example, we have our A mu nu, but we also have this eta function. This is an arbitrary function of the spacetime. And this is what we're adding to right here. Okay? So nothing much is happening. We're really just adding, we have this function on the spacetime. This is a scalar function. This is a scalar field. And we're really just adding it to our original field, our original 4-vector field. Okay? So our Maxwell Lagrangian, as we recall, looks like this without the mass term in it. When we set m equal to 0, we just get 1/4 F mu nu, and that's this right here. We've established that the 2 tensors, when we write them out in their entirety, just in terms of the just in terms of the 4 potential, we get this. And then I'm doing nothing different here except for the fact that I'm putting these primes on here. And these primes are right here, right? I'll make these a little bit like that. But that's just the transformed 4 vector. And what we can do now is we could take, so if we know that this is what the transformed 4 vector equals right here, then we can put that in wherever we see a 4 potential, or a 4 vector. Right, so we're doing that right here, 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 and here, and we're keeping those indices. Right, so we have the mu at the bottom here, the nu at the top, nu at the bottom, and nu at the top here. Okay. And then we're just multiplying everything out, right? So we have this times this is right here, and then times these two, which is right here. So we're really just doing this times this is right here. Okay, and then we have this times this, which is right here, and then this times this, which is, this times this actually. Right, so we're doing this, these two times this, and then here is going to be these two times this, and you can see how this goes, right? So what we're going to get out of here is 4 terms, so that's these 4, and then minus, so here's that minus, these 4 terms, and when we distribute that minus, we get all of this right here, okay? And then what we do is, again, something very simple. We just change dummy indices. We'll change the dummy indices down here. So if you can't tell, this is a mu now and this is a nu. So I'm swapping these two. And you're going to do the same here. So what we end up with is, well, we say that this here looks an awful lot like this. Right, so we can cancel those out. And then this here looks an awful lot like this. So we can cancel those out. And we could see that this here looks an awful lot like this. And so we can cancel those out. And what we're left with is our transformed Maxwell Lagrangian. So they're transformed, that equals -1/4. Let's see here, d mu a nu d mu a nu minus d mu a nu d mu a mu. And what does this look like? Well, this looks like this right here. Nothing changed. Nothing changed when we made this transformation right here. Something would have changed if we had the m term, right? Because the m term has, if you remember, the m term looked like this. My apologies, my iPad bugged out for a second. Anyways, we were at a point where we had said, we were in the middle of talking about the m term. The m term looked like this. And if we would have transformed these two things, then the Lagrangian, you could test this out for yourself, the Lagrangian wouldn't have been the same after having done that transformation. Anyways, so what we can conclude here is that so the Maxwell Lagrangian transformed is equal to the Maxwell Lagrangian not transformed. And this means that the gauge symmetry, this gauge symmetry here, or this gauge transformation, right, leaves a gauge symmetry. And this is a feature of a massless gauge field. So when we say massless, that's when m equals 0. So that's important to note. We have that. Therefore, this gauge symmetry is a feature of the massless gauge field. Okay, this is important. I will box this. This is an important concept to understand. So this means that we can use this sort of freedom within our gauge field, A mu, right? So our gauge field again is A mu, to make sure that we are only working with configurations where this condition holds. If you recall, so we can always shift our field by this scalar so that this is true because our Lagrangian is always invariant under any shift in our under any shift in some scalar function. Okay. And again, for a massless gauge field, the dispersion relation, well, the dispersion relation was m squared equaled k mu, right? But if m is 0, for in this massless case, we get that 0 equals f, or not f, k mu. And so what does this mean? Well, this means that 0 is equal to kt minus kx minus ky minus kz. And if our gauge field is traveling in one direction, we could just say the z direction. Then these two are 0, since the momentum in x and y is 0. And we can say, therefore, that kz squared is equal to kt squared. So kz is equal to kt. And this can also be important to know, because for this massless gauge field, this means, again, if we're picturing this in our heads, this means that we have the momentum of our particle that's described, of our photon, for example. Photons are massless, they're described by a gauge field. The momentum as it travels in the z direction is equal to the time component, or the angular momentum of the photon as it's traveling, because we have our linear momentum, which is described by the spatial momenta, and then our angular momentum is described here. Okay. And what does this mean? This means that if we recall a mu x mu, if we break this down into our space-time structure and our internal structure and our space-time structure. If you recall, this is what's called the internal structure of our space-time. This is called the space-time structure. This means that E mu, or epsilon mu, is actually a vector. It's actually a basis vector in which it looks like this. And we can pick another one that looks like this. Oops. And the reason for that is because we have this freedom to choose whatever we want for our x direction, or our momentum in the x direction, and our momentum in the y direction, if the only constraint here is this right here. Okay. We have another internal structure to our space-time that we can call, that the book calls EL. This is the longitudinal polarization vector. And this is a vector, and you can find out for yourself that it looks like this. Okay. This means that on our space-time, we have these, you can sort of think of them as these little basis vectors. These little basis vectors are longitudinal, like that. We have these little basis vectors at each point in space, and the vector, the 4 potential vector within that, I'll do it like this, the 4 potential vector, which is a mu, exists as a combination of these polarization vectors as it's traveling throughout space-time. And as it's traveling throughout space-time, it's moving in it's moving, and the components of this object are moving in such a way that it can be described in terms of these polarization vectors. And these are the polarization vectors that we get. Okay. Before I move on, these two here, these are called transverse polarization vectors. And this one here is called the longitudinal polarization vector. Okay. And so what we have, the picture that we have now is a field with a 4 potential vector on that field. And that 4 potential vector field is described by a Lagrangian. And that Lagrangian can be rendered invariant if this is a massless gauge field. In other words, if the particle that this field is describing has no mass, then we get these polarization vectors, and we get gauge symmetry. So I'll write that down. If our A mu field is massless, we get these polarization vectors and gauge symmetry. Okay. Again, the longitudinal, so this is the longitudinal polarization vector. And these are the transverse polarization vectors. The longitudinal polarization vector is, again, the polarization vector that describes the constraint, and was the constraint here, right there, because this is our z component and this is our time component. Okay, so we have that, and I believe now I'm pushing a little bit on 20 minutes. The book goes a little bit more in depth here. The book covers, it basically gives an example. It says, okay, let's suppose our A mu nu has this structure. A mu nu is a function of x mu, and it has, again, our polarization vectors, which determine the internal structure of our space-time. And our f, this function right here, it says, let's suppose that is equal to the following function: e to the I k mu x mu. Okay. And so, just as a quick example, A mu nu in the longitudinal direction as a function of x mu is 1, 0, 0, 1, e I to the k mu x mu plus I over k z d mu e to the I k mu x mu. All right, so how do I get that? Well, if we're just traveling in the z direction, and this is a derivative, then what we have is we're really just bringing the z component. This is a spatial derivative. We're really just bringing that out here, the spatial derivative, or the spatial part, the part that's not 0. And we also have the constant I that we're bringing over. Okay. And then what we can do is, oh wait, no, my bad. That makes no sense. It's proposing that this I over k z. So when we do the derivative, right, so I messed up there a little bit. So when we do the derivative, we actually get I squared over kz. And we get e2, actually we get kz, k mu, e to the I, k mu x mu. Okay, so bring the k mu over. Now, again, I squared is just -1, and the k mu becomes, so we get 1 over kz, and we got kz 0, kz, right, because this is our 4 vector. This here's our 4 vector, and since we're only moving in the 0 component and in the z component, we have this right here, and of course we also want this other part, 1, 0, 0, 1, e to the I k mu x mu, and then we also have our e to the I k mu x mu. Okay, and then we get ultimately that our AL mu is equal to this right here, because this will cancel with these. We get that, and then this has to be a minus sign. My bad. And so we get that this is a 0 vector. So the longitudinal component goes to 0. When, again, the longitudinal component goes to 0 when we stipulate that this is a solution to our Klein-Gordon equation. So we have this oscillatory behavior, right? We have this seems arbitrary, but when we make this, again, this means that we've come up with a 4 potential. We've come up with a 4 potential vector that is that will go to 0. All the components will go to 0 when we, in the longitudinal component, or in the longitudinal direction, right? So that is all fine and good. The last thing I want to go over is the general solution to the Proca Maxwell equations. So the general solution looks like this: A mu x mu equals a sum over the polarizations, right? So we're labeling our polarizations with R, and we're going to N. And then we have an integral, and we sum over all possible plane waves with their various momenta. Right. We have this normalization factor, and then here we go. So we're starting off with our polarization vectors, and then we have numbers or weights on these waves that travel in one direction, given by that minus ik. And then again, we just have polarization vectors. And then these numbers, if we're making this complex, or if these are complex numbers, right? These are complex numbers. So the complex numbers are weights on waves going in the opposite direction. Right, so what does this mean? This means we're summing over all possible polarizations, and we're summing over all possible plane waves. Okay. These are just coefficients or weights, if you will, on the plane waves, and these here are the polarizations also. And then we have this normalization factor. So this is the general solution. So what I wrote up here was the general solution to the Proca equation. Okay, and there we have it. We have finished chapter 5. So the next is chapter 6. Chapter 6 covers, chapter 6 is going to start covering interactions. Again, we're talking classical fields, but then right after chapter 6 is when we start getting what we came for. I know you came here for quantum field theory. This is just how it goes, right? So most quantum field theory books will touch over the classical first for like the first 2 or 3 chapters. This book happens to go over classical for the first 5 chapters. And the reason for that, again, is because this is a very student-friendly introduction. It goes over quantum field theory in sort of a slow pace, so that when you do hit the books that cover quantum field theory hard, like Peskin and Schroeder, it becomes actually a lot easier to understand those books. And so yeah, so I don't want to go too far into this, but this is we're coming to the end of chapter 5, and I believe I'm coming close to 20 lectures now. I'm kind of proud of myself. And so I think the next one is going to be lecture 20. And yeah, so I hope to see you guys talking about interactions. So without further ado, let's go ahead and get started on chapter 6 in the next video.